how can mankind turn any non-habitable planet into a flower garden? For example, this is Mars at present, and this is what Mars will look like after going through all the stages of terraforming. Now you'll find out not only about all stages of the planet change, what difficulties we will face with the way of their solution, but also will tell you what organisms are able to survive in the most extreme conditions. What plants will help us make the atmosphere of any planet breathable? But for an example, we'll take the process of transformation not only Mars, but also the hottest planet of the solar system, Venus, and the icy Saturn satellite Titan. So, what inputs do we have? Mars is a planet without a magnetic field, with an incredibly rarefied, dry, cold, and poisonous atmosphere, and an average temperature of -63 degrees Celsius. Venus is a hellish scorcher with a temperature of over 500 degrees Celsius, with a pressure 92 times that of Earth. And Titan is Saturn's largest moon with methane oceans and a perpetual winter of -179 degrees Celsius. Let's start with the first thing. We need a magnetic field to start the transformation. If Titan's magnetic field isn't bad enough, Venus and Mars are much worse. So first we have to build a strong magnetosphere. Otherwise, the solar winds will simply sweep away the atmosphere we've just created. But how can we do that? NASA's Director of Planetary Science, Jim Green, argues that launching a magnetic shield into a stable orbit between the celestial body and the Sun at the Lagrangian point L1 could help create a shield that would leave the planet in a relatively protected tail of the magnetic field, which would allow us first not to worry about solar radiation, and secondly, quietly engaged in creating a livable atmosphere. When thinking about how to change the atmosphere of a planet, we need to remember what kind of result we need. If Mars and Titan needs to be warmed up, then with Venus, it's the opposite. We need to lower its temperature by 20 times to an average of 25 degrees Celsius. And in all cases, we'll use a few basic methods: orbital mirrors, factories, and photosynthesizing organisms and plants. Let's break down all the methods in more detail. In the case of Mars and Titan, orbital mirrors will be used to directly heat the surface. Located near the poles, these mirrors will be able to concentrate the sun's rays to a single point on the surface, heating the surface and melting Mars's ice cover. With Titan, a more interesting approach will be tried. By directing the rays to one specific location, we can ignite one liquid methane ocean, for example Ligeia Mare, and cause a greenhouse effect sufficient to chain reaction with other lakes and so on, eventually heating the planet above or near 0 degrees Celsius, enough to melt rock-hard water and create a water world. At this time, mirrors in Venus's orbit, by contrast, will not have to direct the sun's rays towards the planet, but reflect and direct them into space, cooling down the planet and reducing the greenhouse effect. Unfortunately, using only orbital mirrors will not achieve a great effect, so the next right step will be to build a huge number of stations that will be able to absorb carbon dioxide and convert it into oxygen, significantly reducing the hellish temperature that is in Venus. Mars and Titan don't need to be cooled, as they are already insanely cold worlds, so on their surfaces we should focus on building the factories that already exist on Earth to start the process of massively releasing carbon dioxide into the atmosphere, warming the planets more and more. And funny, what bothers us on Earth, CO2 emissions, global warming, in the process of terraforming other worlds could be an extremely useful thing to do. After a while, when the temperature of the planets is not so extreme, but the atmosphere is still full of carbon dioxide, there'll be a need to convert CO2 into oxygen. So the right thing to do is to repopulate the planets with photosynthetic plants and microorganisms that can survive in difficult conditions. Whole colonies of cyanobacteria, plants, and algae that produce oxygen on planetary soil will be utilized. Of the microorganisms in particular are the tardigrade, or as they're also known as water bears. They're able to withstand incredibly low and extremely high temperatures, high levels of radiation, incredible pressure, lack of moisture for more than 100 years, and finally, open space. These are the creatures that will be the first real colonizers of space. After a certain amount of time, we have a very dense atmosphere, with favorable temperatures and the first settlers, and therefore the need for water. If everything is clear with Mars, ice poles where we direct sunlight and use the greenhouse effect to melt them, What about Venus, which has no hint of water even in the gas state, or Titan, which has methane instead of oceans of water? Let's talk about Venus first. There are various ways to bring oceans of water to Venus. One obvious option would be to transport water from Earth's seas and oceans by cargo spacecraft. But unfortunately, this option is more than unrealistic because to achieve the desired effect, we would have to transport about 30 million cubic kilometers of water. And even with the calculation that we would have a huge fleet of 1,000 spacecraft, each of which could carry a payload of 1,000 tons, it would take 30 billion flights to transport this amount of material. So we move from that method to another possibility, to transport only hydrogen, and not necessarily from the Earth. And the reason why we should choose this method is that a water molecule consists of 2 hydrogen atoms and 1 oxygen atom. But the latter is 16 times heavier than the hydrogen atom. Thus, the mass of material delivered to Venus will be reduced by 90%. In consequence, water can be obtained as a result of a chemical reaction of transported hydrogen with the remaining carbon dioxide in the atmosphere of Venus. Hydrogen itself could be created on Earth by splitting water molecules into their constituent elements. Or it could be obtained elsewhere. For example, it could be collected by scooping it up in an orbital ring from the atmosphere of one of the giant planets in the outer solar system, and delivered to Venus by spacecraft. As for Titan, we can use the same method as with Venus. Fortunately, in this case, it'll be much more favorable because it is such a close distance to Saturn. Transportation of hydrogen will be cheaper in the first place and faster in the second place, which is a major plus. People should also look at another satellite nearby, Enceladus. It's the 6th largest satellite of Saturn, the average radius of which is only 0.04 Earth radius, but its surface is completely covered with ice, and under it a whole ocean of salt water. According to NASA scientists, there's geological activity on Enceladus. Geysers are beating, there are constant emissions of water vapor, ice flakes, and even microscopic grains of sand. All of this tells us we have another place to get enough water to change Titan, and besides, the minimum distance between the 2 satellites in the period of convergence may be just over 1 million kilometers, which is an extremely close distance even by the standards of current technology. For comparison, the distance between the Earth and the Moon is 384,000 kilometers, which is only 2.6 times less than from Titan to Enceladus. So, based on all this information, you might think that this is how we'll get water for its subsequent delivery to Titan. But it's not so clear, because at first glance it might seem that only methane can be found on Titan's surface. And it is. But if you look at the interior, it's much more interesting. Just beneath the icy crust of methane is a whole ocean of liquid water, and underneath it is even a larger amount of water ice, so it's possible to extract large amounts of water on Titan itself. The challenge is just to pump it up from the ground to the surface and figure out what we're gonna do with so much methane. The answer to this question is that since methane is the most convenient fuel for reusable rockets, we can build a huge number of refueling stations that will fill up and eventually fuel a huge fleet of spaceships. This would firstly make it cheaper to fly in the outer part of the solar system to minimize costs, and secondly move inland, starting to develop and build our bases on the satellites of Neptune and Uranus. The chemical composition of the atmosphere is close to the Earth's. The atmosphere is stratified, the ozone layer appears, and what's not a little important, the temperature stabilizes. After that, the formed hydrosphere appears. Oceans, seas, rivers begin to flow. Introduced ice melts, atmospheric water vapor condenses, water collects in natural lowlands, thus forming reservoirs. The first settlers are no longer concerned with the formation of a global climate, but with climatic conditions on individual surface areas. As the atmospheric pressure and temperature regime gradually come to normal values for us, we start building cities under light domes, with artificial atmosphere suitable for breathing of the first settlers. This is done because the atmosphere of the planet is not yet adapted for full-fledged breathing, but on the surface it's already possible to be not in a spacesuit, but in a light suit and a breathing mask. The construction of channels to regulate the flow of water into reservoirs, draining some areas and reclamation of others begins. Fine-tuning of the entire ecosystem begins. At this stage, the reproduction of organisms that were brought in earlier to modify the atmosphere stops. They're replaced by the permanent plant life of the modified Mars, Venus, and Titan. Now that we have altered these worlds, turning them into an Earth-like paradise, people in huge numbers are beginning to arrive and establish giant colonies and cities of the future. The ideal outcome of terraforming is a global self-sustaining ecosystem, capable of providing humanity with the minimum necessary conditions for living: food, materials for clothing, and housing construction, even in case of loss of communication with the Earth, the donor planet, or the death of our civilization. Different researchers give different terms necessary for terraforming at this or that planet. The most optimistic forecast as a rule for Mars, it's a couple of hundred years from the beginning of the transformation. According to other calculations, we'll have to wait up to 1,000 years. It may be a long process, but if you look at the human history, you realize that the prospect of being in a world in a couple of hundred years where Earth is not the only home for humanity doesn't seem that long away. Just imagine, the Egyptian pyramids, the Roman Empire, the Middle Ages are much farther away from us than the conquest of the solar system. Well, while such achievements seem something far away, I suggest you watch a video about how we can colonize the nearest exoplanet to us, Proxima Centauri b.